Hi guys, thank you for joining me today. In this video, I will go through the method of superposition method. What is the meaning of superposition method? Superposition is used to solve the combined effect. If we have a problem under the effect of applied force and the temperature at the same time, both of them at the same time. So each effect is calculated alone. I mean, the effect of fluid is calculated alone and the effect of temperature is calculated alone. I will solve the problem two times. The first one under the effect of the applied load and the second one under the effect of the temperature. Then the final effect in terms of stress or deformation will be the summation of the two effects. This method will be valid if we are still in the linear stage. If we go forward to nonlinear or plastic stage or plastic behavior, the superposition method will not work. But this is outside the scope of this course. So right now, for example, I have a problem, and this problem under the effect of applied force. At the same time, we have a change in temperature. In the previous videos, I solved problems, examples, under the effect of temperature alone. I solved other examples under the effect of applied force alone. In this video, I am going to solve a problem under the two effects at the same time. The first example, we have at 50 degrees Fahrenheit, the gap between NDC and D is 0.01 inch. Without any change of temperature, without any applied force. We need to figure out the support reactions at A and D when we have applied force P equal 100 kip and the temperature increase from 50 Fahrenheit to 92 degree Fahrenheit. Does that make sense? The material for this assembly is solid steel cylinders with Young's modulus E steel equal 29 times 10 to power 3 and the coefficient of thermal expansion alpha steel equal 6.6 times 10 to power negative 6. So right now we have two combinations. We have a change in temperature equal not 92, not 50, but it's 92 Fahrenheit minus 50. So the change of temperature will be 42 degree Fahrenheit. This is the value of delta T. And we have applied force P equal 100 kib. So how can I solve this problem? Make sure you understand the method of superposition. I'm gonna assume the effect of temperature exists alone and the change of the applied force existing alone. I will solve the problem two times, one under the effect of change of temperature and the second one under the effect of the applied force. Which one I'm gonna start with, it's up to you. That's fine. It's up to you. So I will start with temperature, effect of temperature. First of all, I would like to make sure the end C will hit the wall at D. So this part, assembly to this part, I'm gonna assume it free. This is A, B, C. We have a change of temperature equal 42 degree Fahrenheit. So delta thermal, the axial deformation due to the effect of change of temperature equal alpha delta T time L. The value of alpha for this material, 6.6 times 10 to power negative 6. Change of temperature equal 42. The total length of this member, the total is 2 feet. I'm gonna multiply it by 12 to be an inch. So L is the total. This one is 1 feet. And this one is 1 feet. So the total will be 2 feet. I'm gonna multiply it by 12 to be an inch. So the total thermal axial deformation, 6.6 times 10 to power negative 6 times 42 times 2 times 12. I got 0.00665 inch. Does that make sense? This change of temperature, this change in the axial deformation due to temperature is smaller than the gap between the end C and D. So the wall will not hit, the shaft will not hit the wall. In this case, sigma in part AB will be 0. Sigma in part BC will be 0. Reaction at A will be 0. Reaction at D will be 0 due to the effect of temperature. Due to the effect of temperature, no change. No stress, no thermal stress. This one due to temperature, due to temperature, due to temperature, due to temperature. Why? Because the effect of temperature was not prevented. The the shaft is free to expand. Why? Because this end will expand 0.00665, which is smaller than the free gap between the end and the end of the shaft and the wall. That means the shaft is free to expand, no prevention. So no reaction, no thermal stress, nothing. This is the first one. The second one, I am going to consider the effect of the applied load. Here is the shaft. Here is this part. Here is the applied load, 100 kip. So I'm gonna assume the shaft is free at this end C. This is B, this is A. So what is the change of the axial deformation in part AB? Will equal P L divided by A E. The applied force in this part, if you did cut here and you take the right part, so the force will be tension 100 kip. The length of this part AB is 1 feet. I'm gonna multiply it by 12 to be an inch. What is the cross-section area of part AB? The diameter is 1.5 inch, so it will be pi divide 4 times 1.5 square. What is the Young's modulus of the material of this part? Equal 29 times 10 to power 3. Looks like everything is matching. So the unit of this one is kip, this one in inch, this one in inch square, this one in kib per inch square. We are good. So the final elongation of this part AB will be 0.023 inch. Still figuring out the elongation in part BC equal PL divided by AE for part BC. This one will be 0. Why? Because if you did cut here and used the right part, no force. Time L divided by AE, whatever these values, the elongation will be 0. So under the effect of the applied force, this end will move point O, how much? 23. So this is the elongation. However, we have a wall here at D with this gap only 0.01 inch. So this part will be prevented. The end of the shaft will hit the wall at D. That means we will expect a reaction here from the wall to the shaft, reaction at D, and we will have another reaction here at A. And this is your new problem. So the first step I did here, the total elongation equal 0.023 plus 0 equal 0.023 inch, which is greater than 0.01 inch. So the end of the shaft will hit the wall. That means we will have stresses, we will have reactions, and we will have everything. So let's start to resolve the problem for the new situation. The first situation, I assumed it's a free at the end, but we have this end hit the wall, so we have another situation which is a correct one. So we have part AB and we have part BD. So for part AB, the elongation of this part will equal PL divided by AE. The applied force in this part, if you did cut and you consider the left part, it will be the reaction RE. The length of this part is 1 feet. I'm gonna multiply it by 12 to be an inch. Area by divide 4 times 1.5 square, the diameter of this part, Young's modulus 29 times 10 to power 3. What is this value? Equal 0.00023 reaction RD. How much axial deformation in part BD? So we have reaction if you did cut here and you used the right part, we will have reaction RD. So the applied force in this part will be reaction RD. This one is tension in AB. This one will be compression R in D. The length of this part, 1 feet. I'm gonna multiply it by 12 to be an inch. The area of this part by divide 4 times diameter of this part 0.75 square. Young's modulus of the material 29 times 10 to power 3. The elongation in this part will be, or the contraction because it's a compression, negative 0.000936 reaction at D. Keep in your mind the axial deformation in part AB plus the axial deformation in part BD must equal how much? The only allowable deformation is this gap, 0.01 inch. After this, no allowable for any axial deformation. So it will be 0.01 inch, the gap between the end of the shaft and the wall. So 0.00023 reaction at A plus negative 0.00936 reaction at D must equal 0.01 inch. Keep in your mind the reaction, if you apply summation f of x equals 0, so the reaction at A in negative, the reaction at D in negative will equal or plus 100 will equal 0. So I can say the first equation, reaction at A plus reaction at D will equal 100. So this is the first one, first equation. This is the second one. So R at A plus R at D equal 100. So I can say reaction at A equal 100 minus reaction at D. I can use this equation in this one, so I can remove 0.00023. I can remove RA and put 100 minus RD plus negative 0.0000936 RD equal 0.01. So I can figure out the reaction at D, and then just a moment. Reaction at D and then reaction at A. So the reaction at D, I think, excuse me, 11.15 kip. If you subtract this RD from 100, the reaction at A will be 88.85 kip. Once you get the reactions at A and D, I can say this is the final problem. We have hitting here the wall. We will have reaction here at D equal 11.15. We have applied force here 100, and we have a reaction here 88.85. This is for the applied force. Keep in your mind, for the effect of temperature, we are lucky. We don't have any hitting between the end of the shaft and the wall. So the reaction here was 0, the reaction here was 0, and this is a change of temperature equal 42 degree Fahrenheit. So the final reaction, keep in your mind, if we have values here, we will add both of them. So the final reaction at this end will be 15.5 I'm sorry, 11.15 plus 0 equal 11.15. The final reaction here will be 88.85 plus 0 will equal 88.85. This is the final reactions here. If you would like to figure out the stresses, stress in part AB will equal the applied force in this part will be tension 88.85 divided by divide 4 times 1.5 square. You can get the stress case psi, tensile stress. Stress in part BC will equal the applied force compression 11.15 kib divided by the area of this part 0.75 square. You can get the stress case psi will be compressive stress. That makes sense? So the superposition in this example, we have effect of temperature, we have effect of applied force, so I will consider each alone. The effect of temperature, you are lucky, I consider the effect of temperature, it's free to expand, the expansion equal 0.00665, which is smaller than the end gap, so no hitting to the wall, so no restriction for the elongation, so no stress, no reaction, nothing, due to the effect of temperature. But for the applied force, I consider first it's free. So I figured out that the end of the shaft will hit the wall. So we will have reactions and we will have stresses. The reaction only for the part that will be prevented. That makes sense? So by the end, I can say the axial deformation in part AB plus the axial deformation in part BD only allow to elongate 0.01. So I set up an equation which is called compatibility equation, and we have already equation from summation f of x equals 0. I solved the two equations together to figure out the reactions at the two walls. These reactions only due to applied load. So if we have something from temperature, I have to put it here, I have to put it here. So the final reaction will be this one plus this one. This one plus this one. This is the final reactions. That makes sense? We have another example. We have composite column. This composite column is subjected to an axial compressive force 200 kilonewton and the increase in temperature equal 50 degrees Celsius. We need to figure out what is the stresses developed in steel and the concrete and what is the change, the final change in the length. So looks like we have two effects, load 200 kilonewton and the temperature change. So first of all, I will solve this problem two times. One due to the effect of temperature and the second one due to the effect of the applied load. Which one is first? It's up to you. But before starting, I would like to figure out what will be the area of concrete equal the inner diameter, the inner area of the circle by divide 4 times 60 square. The area of steel, which equal by divide 4, the outer circle 70 square minus the inner circle 60 square. So by divide 4 times 60 square, I got 2827.4 inches square. (1,021 inches square). This is the area of steel. So let's start with the effect of load. Effect of load in composite column, go back to the previous videos. I will say the steel will share a little bit. The concrete will share a little bit of the applied load. If you added the part shared by steel and plus the part shared by concrete, both of them must equal the applied load, 200 kilonewton. That makes sense. The part shared by steel will cause axial deformation delta S, which equal PLAE for steel. The part shared by concrete will cause delta concrete, PL divided by AE for concrete. Since the two materials are working as one unit, no one will leave the other one, so both of them will contract with the same amount. So delta steel must equal delta concrete. So PLAE for steel must equal PL over AE for concrete. Keep in your mind the length of steel and the length of concrete, both of them are equal. This one is 4,000, I'm sorry, 4,000 millimeter. So let's set up another equation. The applied load on the steel divided by area of steel 1021 time E steel 200 gigapascal. I will multiply it by 1000 to be megapascal. Actually, I can leave it in gigapascal, or it's not a big deal because we have equal equations. So if you keep it 200, that's fine. Equal P concrete divided by area concrete, which is 2,800, I think 27.4 time E concrete, which equal 25 gigapascal. It's not a big deal to change this one to megapascal and this one to megapascal because both of them are equal. So what you are doing here will be the same on the other side. So B steel will equal it will be B steel equal 2.88 B concrete. This is the second equation, and this one was the first one. If you solve the two equations together, I can remove here B steel and put 2.88 P concrete. So I can say B concrete equal and B steel equal. So plus one. So B concrete will be 51.4 kip. And B steel will be 148. Let me check it one more time. 200 minus 51.4. It will be 148.6 kip. That makes sense? The stress on concrete will be compressive stress. The stress on steel will be compressive stress. The applied force on concrete, 51.4 time 1000 to be, I'm sorry, this is not in kip. This one in kilonewton. I will multiply it by 1000 to be in Newton divided by the area of concrete, which was 2827.4. The stress, the compressive stress in steel will be 148.6 times 1000 divided by the area of steel 1021. So by the end, the effect of the applied load on the composite column, stress on steel equal negative, stress on concrete will be negative. How much? For concrete, 51.4 times 1000 divided by 2827.4. I got negative 18.18 megapascal. For steel, it will be 148.6 times 1000 divided by 1021. I got negative 145.5 megapascal. Both of them are compressive stress due to the effect of the applied load. And keep in your mind, the final axial deformation in the column will be contraction. So the length of the column will decrease. How much? One of them, delta steel or delta concrete, one of them. It's up to you. So I can say PL divided by AE for steel or for concrete. So the applied load for steel, 148.6. The length, 4,000 millimeter. The area of steel, 1,021. E for steel was 200 gigapascal. In this one, I have to make sure the units are matching. This one in kilonewton, this one in millimeter, this one in millimeter square, this one is gigapascal. So I have to adjust. I can keep it in gigapascal since this one in kilonewton. Or you can multiply this one by 1000 and this one by 1000. It will be the same, no change. 148.6 times 4000 divided by 1021 times 200. I got 2.91 millimeter. Contraction. Contraction means negative value. Why this one is negative value? Because the applied force is compression force. This effect due to the load. I need to resolve the problem one more time to figure out the effect of temperature. We have a change of temperature based on the problem equal 50 degrees Celsius. So do you remember how we can solve the composite column under the effect of temperature? This is the concrete. And we have this part for steel. I'm gonna assume each component will expand freely. So concrete will expand. It's not too much, I'm sorry. It should be a little bit. This expand for concrete due to temperature equal alpha for concrete, change of temperature delta T time length of concrete. For concrete, the alpha is given 11 times 10 to power negative 6. Change of temperature is given 50. The length of concrete equal 4,000 millimeter. 4,000, the length of the composite column. So we will have it change. If the concrete is free to expand, 11 times 10 to power negative 6 times 50 times 4,000, it will be 2.2 millimeter. If we assume the steel is free to expand, the steel will expand too much. How much? Delta steel due to temperature equal alpha for steel, change of temperature delta T, length of steel. Alpha for steel equal 17 times 10 to power negative 6. Change of temperature equal 50. The length of the steel equal the length of the composite column, 4,000. So the steel will expand 3.4 millimeter. That means we will have difference between the expansion of steel and the expansion of concrete equal 3.4 minus 2.2 equal 1.2 millimeter. This difference will not happen. This difference will not happen. So this difference equal 1.2 millimeter. As I mentioned, this difference will not happen. So what will happen? We should expect an applied force P pushing the steel down by delta steel. And the same force P pulling the concrete up. Why the same force? To maintain summation F of I equals 0. So the concrete will move up by delta concrete until the two materials reach to each other. Keep in your mind the distance that the steel moved down plus the distance that the concrete moved up. The two distance, if you add both of them, will equal the original difference between the two material, 1.2 millimeter. Keep in your mind, the steel moved down due to the effect of the applied force P, L steel divided by area steel, E steel. Plus delta concrete, we are talking about right now about a force P. So P in the concrete, the same P, L concrete divided by A concrete, E concrete, equal 1.2. Go ahead and put your numbers. I don't know what is the applied force, but I know what is the length of the steel, 4,000, area of steel, 1,021, E for steel equal 200 gigapascal. This one in kilonewton, so I will keep this one in kilonewton per millimeter square, which is gigapascal. Plus P time L concrete 4,000 divided by area concrete 2,827.4, I think. 2,827.4 time E concrete equal 25 gigapascal equal 1.2 millimeter. I think we are good with the unit. So the only unknown in this equation is the applied force P. So 4,000 divided by 1,021 times 200 plus 4,000 divided by 2,827.4 times 25. I think the applied force will be 15.75 kilonewton. That makes sense? So keep in your mind, this force will push the steel down. So we will have compressive stress in steel equal the applied force divided by the area of steel will give you compressive stress. How much? I will multiply it by 1,000 to be in Newton. So the value will be 15.4 megapascal. Keep in your mind this force trying to pull the concrete up to reach to the same level for the steel. So it will be tension 15.75 times 1,000 to be in Newton divided by 2,827.4. So the stress will be positive. 5.57 megapascal. Keep in your mind, the final elongation due to temperature in the column. I'm talking about temperature. So the original shape was here. The final shape became here. We have two options. I can say the free elongation in steel minus the new contraction in steel, or the free elongation of concrete plus the new elongation in concrete. It's up to you. So I can say delta steel, which was free, minus the new contraction in steel, or the free elongation in concrete due to temperature plus the new elongation in concrete, this or this. So let's do the steel. So the free elongation of steel was 3.4 millimeter. Minus the delta in steel. Delta in steel is this one. P steel, or P, because we don't have P steel and P concrete, P L steel divided by A steel, E steel. So 3.4 millimeter minus the applied force 15.75 time 4,000, the L of steel, which is the length of the composite column, area steel 1021 gigapascal. I'm sorry, E steel equal to 100 gigapascal. I did not change gigapascal because this one in kilonewton. So the final elongation in the composite column will be 3.09 millimeter. This is the effect of temperature. What is the total effect? Load plus temperature. Sigma steel, sigma concrete. For the applied load, the stress in steel was negative 145.5. And the stress in steel due to temperature was negative 15.4. So the final stress in steel will be negative 160.9 megapascal. The stress in concrete due to the applied load was, you remember, negative 18.18. And the stress in concrete due to the temperature, the first one due to the applied load, the second one due to temperature, positive 5.57. So the final will be negative 12.61 megapascal. The final change in the axial deformation in the composite column due to temperature and the applied load, keep in your mind. Due to the applied load, we have contraction in the column, negative 2.91 millimeter. But due to the effect of temperature, we have elongation in the column, positive means elongation, 3.09 millimeter. So the final axial deformation in the column will be positive 0.18 millimeter. Positive means elongation. So the length of the column will increase by 0.18 millimeter. The final stress or the total stress in the steel will be negative 160.9. the final stress or the total stress in the concrete will be negative 12.61. This effect due to the applied load and the temperature. That makes sense? So the method of superposition means you have to solve your problem 2 times. The first one due to temperature, the second one due to the applied load, then go ahead and add the effect of temperature plus the effect of the applied load together by the end of the problem.